Okay, so we'll start the second part of this morning section. First one will be given by Dr.Ryo Mizuta from MRI. This talk is going to talk about climate projection using MRI AGCM3 with 20 and 60 kilometer deep.
Okay, my talk is about the climate projections using MRI AGCM with 20 kilometers and 60 kilometers. So thank you for inviting me to this interesting workshop, and I am very happy to see here that many people are using our model output here in Taiwan. Okay, so this talk is focused on today we focus on the ensemble experiments to evaluate the uncertainty of the climate projection. So we have been developing a high-resolution atmospheric global model for over 10 years. High-resolution model, by using high-resolution model, a small-scale, we can simulate small-scale structures such as tropical cyclones and localized phenomena associated with small-scale topography. So this is a very big merit. But when we want to see the climatic change of these phenomena by doing long-term simulations over several decades, it requires good representation of these things, these many things. One is physical structures of small-scale phenomena, and also statistical climate of these phenomena. And in addition, we need a good representation of global scale climatology. So it's a very complicated task. So the MRI AGCM3 has been developed for a high resolution simulation for the Earth simulator. This has been developed from JMA operational numerical weather prediction model. After some version ups, we are now using version 3.2. In this version, many aspects are improved mainly by introducing a new parameterization scheme and so on. And the improvement is seen mainly in the reduction of the model biases of these things like insufficient precipitation amount over the Western Pacific, or geographical distribution of tropical cyclones. So, and in addition, in this version, the resolution dependence in terms of global scale climate is also reduced. So we use this model for ensemble simulations using lower resolution version of this model. This is just a quick look at the model climate using emit type simulations using the observed SSD from large scale. This is JJ precipitation. The top panel is the observation, and the middle panel is the current model. For the left panel is for the global, and the right panel is for the Asian region. So you can see the model can simulate well the precipitation pattern from western coast of India, the Bay of Bengal, and Philippine Sea, and as well as Eastern Asian monsoon. And in addition, very small scale topographic effect in inland area of China. And this is from large scale, and this is small scale model climate. This is intensity of the PDF of intensity of tropical cyclone. The horizontal axis is the maximum wind speed. So the blue line is the observation, and the green line is the previous model. The previous model has insufficient tropical cyclone, intense tropical cyclone, but in this model, the model can simulate also intense cyclones, especially in the western North Pacific. So, using this model, we have been doing time-size experiments. So we take project SST change from CMIP atmosphere ocean coupled model to give lower boundary condition of the atmospheric model, and the output of this model is used for very wide range of applications. And one thing is the study of future change in extreme events by our group, and another thing is the dynamical downscaling by using regional climate model, or in Japan area and also in Taiwan area, and it is also used for the impact assessment of disasters and agriculture and water resources and other things. And in addition, this output is directly used for the regional climate change. These outputs are provided to researchers of each region of these countries to see the climate change over their own countries. So then, this is the settings of the experiments in the previous project in Kakushin program. As the present climate experiment, the AMIP, this is AMIP type experiments using observed sea surface temperature and sea ice concentration. And as the future climate experiment, we use SST warming from the CMIP coupled model, and the SST warming is added to the observed SST and see the response. And but the 20-kilometer model has only a pair of experiments of present day and future climate. So we have been doing the ensemble experiment using 60-kilometer model for evaluating uncertainty of the change. We use 3 types of cumulus convection scheme for the present climate simulation in the 60-kilometer models, and use 4 types of SST change in the future climate simulation. So we have 12 future simulation in the total. When we change the cumulus parameterization scheme, the present climate can start to change, especially in the view of extreme events. So this is one example of cyclone tracks. This is observation, and these are 3 simulations with 60-kilometer models. Basically, 60-kilometer models can simulate very intense cyclones. But in addition, these 3 simulations differ in the intense cyclone simulation. But when we see the future change, this is a global number of tropical cyclone for each 12 simulations, and this is their line, and so in all of the simulations, the cyclone number is decreasing in the global point of view. So this is robust results. And then when we see the regional change, for example, it's in the Western North Pacific, or it's Southern Indian Ocean, the results can change depending on the simulation. The difference is mainly depends on the SST changes shown here, rather than the difference of cumulus parameterization scheme. And this shows the tropical cyclone genesis change and the SST change. The shading is the tropical cyclone genesis frequency, and the contour is the anomaly of SST change. For this is the average of 3 experiments using the same SST change. So these 4 panels show different pattern, and the shading and contours corresponding to each other. So tropical cyclone genesis frequency can be changed, can be depends on the anomaly of SST change. To quantify these results, the variance between the experiments are divided into the factors by a two-way analysis of variance. All the variance between the 12 experiments are divided into the variance by different SST and variance by different convection scheme and residual. So this is results for the tropical cyclone genesis function, genesis frequency. So you can see the spatial distribution of the SST change is a major source of uncertainty in terms of regional change of tropical cyclone genesis frequency. So based on this result, in this current project social program, we have redesigned the ensemble experiments. One thing is just update from using CIMIP3 results to using CIMIP5 results, and another thing is the 20-kilometer model ensemble. So we decided to do 4 SSD ensemble experiments using the 20-kilometer model, and also much more experiments by using 60-kilometer models. We use 60-kilometer model because generations of tropical cyclones needs to be well simulated for the study of extreme events, especially over East Asia. So we cannot use more coarse resolution model. We must use relatively high resolution ensemble experiments. And we also consider more factors of uncertainties. One is uncertainty from scenario uncertainty of greenhouse gas emission. So we use this time for scenario RCP 2.6 and 4.5, 6.0 and 8.5. And also considering uncertainty from different climate models. Large part of uncertainty can be covered by the SSD ensemble experiments, but not all it can be covered. So we are planning running additional experiments to over direct downscaling from three coupled models to 3 regional climate models, but it is not shown today. So this is the diagram of the ensemble experiments. It becomes 3D diagrams. This axis is scenario ensemble, and this axis is ensemble physics scheme. This is cumulus parameterization scheme, and this axis is SSD ensemble, and black circle shows the 20-kilometer experiments. So this is SSD ensemble using RCP 8.5 scenario, and the red points and the blue points shows the ensemble experiments with 60-kilometer model. Red points and blue points from different projects because of budget, but we are doing same setting of simulation, so we can combine these 2 sets of simulation together to see the uncertainty. But the calculation are now ongoing, so I can show you the results today. But I will talk a little bit about the cluster analysis of SSD ensemble. SSD ensemble experiments uses 3 clusters of one mean pattern in addition to the average of all models, using 28 CMIP5 models, of which historical and RCP 2.6 and 4.5 and 8.5 results are available. And the method of cluster analysis is basically same as before, using mean future SSD change from present simulation and future simulation of CMIP5 models, and then they are normalized by the tropical mean to see the pattern, not the magnitude. And the cluster analysis is applied to the patterns by using pattern correlation as a distance between the models. So this figure shows the SSD change from historical experiments to the RCP 8.5 scenario for each CMIP5 models after normalized. So we can see some similar patterns between the models, but some models show very totally different patterns. And this is the results of cluster analysis of these patterns. So we can divide these model results into 3 categories: cluster 1, 2, and 3. And the one interesting thing maybe related to the previous talks is that different models from one same model center can show very similar patterns. So categorized into often categorized into one cluster. For example, this GFDL or MPI, GSS, and hardware center. So yeah, and this is the average of the patterns for each cluster. In the cluster 1, we can see the rather uniform warming in the tropics, just like here. And in the cluster 2, the larger warmings in the tropics and subtropics in the eastern Pacific. And in the cluster 3, larger warmings seen in the northern Indian Ocean and the northwestern Pacific. So the pattern is different here between the clusters. And this is one model results picked up from the previous slides. So this is CCSM4 results, and this is very similar to the cluster 1 average. And this is AGCM3 results and MRI AGCM3 results. They are also similar to the cluster 2 average. And yes, the same things can be said for the GFDL model and the MIROC model. So we may be able to say that these clusters can represent these CMIP5 model results. Okay, so this is a summary. In the previous Kakushin program, the uncertainty of the change by global warming is evaluated by using 6-pictometer ensemble experiments. I just only show the tropical cyclone results, but the global total number is decreasing in all experiments, but the spatial distribution of SSD change is measure source of uncertainty in terms of regional change in the tropical cyclone. Based on these results in this SOSE program, we have redesigned the unsolvable experiments, and these experiments are now ongoing using 4 SSD unsolvable simulations by using the 20-kilometer model and much more ensemble by 60-kilometer model. So that's all for my talk. Thank you.
Thank you. Any question?
Thank you again for the discussion. I'm surprised only 3 clusters, but that's fascinating. Could you explain again how you did the cluster analysis from the start? The 0.5 there.
The cluster analysis is applied to the pattern of the panel, and using pattern correlation between the models as a node distance between the models. If the pattern correlation between the models are large, the distance is small, so we categorize into one group. And yeah, so then repeat it.
This is from the cluster center, the central one.
Yes, cluster centers are calculated by the mean.
Thank you.
Thank you for your answer. I'm also interested in clustering. So, do you think these clustering methods represent some particular phenomena in these modern groups? For example, cluster 3 looks like it represents cluster 2 in treatment. It looks like it emphasizes the El Nino-like warming in the modern community.
Yes. So yes, we apply the cluster analysis for SSD only. So characteristic of pattern of the change of the models with El Nino or La Nina is emphasized in this clustering.
I'm interested also in your analysis of the typhoon frequency behavior, and I think you demonstrated that most of the models indicate or project a decreased number of typhoons. Have you looked into the intensity aspects of these type of hurricanes, whether there is a uniform agreement among models on intensity?
So basically, the intensity is increasing in the results using 20-kilometer model, and also in the 60-kilometer models. But yes, we cannot say much about this because very intense cyclones cannot simulate very well in the 60-kilometer models.
And there is also agreement among the models in terms of intensity?
Yeah, yes.
Any other question?
Just one more. Could you please go back to the previous slide? I was curious about why the frequency of cycle every those configuration is always smaller than the observation in the do you have any speculation on this?
No, I have no idea. It changes very much depending on the parameterization. Just one parameter within one cumulus parameterization scheme. So,
Thank you.
thank you very much.